Hey, hi everyone, this is Vivek, and in this particular video, we're going to talk about Manacher's algorithm. Now, in this particular video, we're going to go through its implementation details as well, and we're going to understand what are some basic usages that you can kind of go through with it. But in general, the main idea of creating this video is to actually make sure that you all are clear on the concept of why Manacher works. Now, for most part of problems, you might not even need to know about like how Manacher works. It just gives you an array which you can use to solve certain degree of problems. But like the idea behind Manacher's algorithm is really cool. The same idea is also used for Z algorithm behind the scenes. The idea of this bounding box and to understand why the whole algorithm works is O of n is actually super cool. So that's what we cover in this particular video. Also, once you understand how this works, you'd be able to implement Manacher algorithms on your own too very easily, right? So that is what is the target for this one, because I've seen many students fearing to be able to not write Manacher algorithms in interviews themselves, and even sometimes in tests and stuff. So that's what we will be covering in this particular video specifically, right? So let's get started with Manacher, right? So what is the basic idea of Manacher algorithm? So essentially you are given a string, let's say B A B B A B B A B C, right? Some string like this. And essentially you have to do certain sort of atomic operations, like find the, like given a particular center, which means let's say you have a center, an odd center. So this is called an odd center, which means the palindromes at this place would be of odd length, right? And then there might be an even center, let's say over here, right? So you would have like palindromes of even length at this place, right? So you can have even larger palindromes at this place, right? And you can find the longest palindrome that happens to be there at a particular center. Like in this case, the longest palindrome will be of length 6, right? And you can also check if a particular L2R is palindrome or not. So that's like two very basic utility that Manacher algorithms gives you, that you can find out these things directly. And you can also check for, let's say, if let's say this is a palindrome, yes or no. If this is a palindrome, no. If this is a palindrome, yes. This is what Manacher algorithms is very neat in returning, right? And all of these things, like these two functions, both of them work in order 1, and Manacher algorithm does a pre-processing which works in O of n. Now in this video, we're going to understand what this O of n pre-processing works like and how you can kind of do these operations in O of 1. That's the agenda of this particular video. Let's get started with how we do that. So the first step of Manacher is generally to do a pre-processing. Now this particular pre-processing is just to make the code a little easier. Reason being is like odd centers and even centers behave a little differently in terms of the edge cases that happens. So like for a odd center, you might have to like kind of, for an even odd center, you might have to handle the edge cases a little differently, for even one a little differently on both the sides. So just to make it like a unified case, what we do is we transform this input over here given to us as a string s into a t string, right? Let's say some s to t string, where we just get like hashes in between every character, and at the start and at the end too, right? That's what we do. So hash b, hash a, hash b, hash b, so on. Like every in between, we are putting up a hash, right? That's what we do. Very straightforward to do, right? So if there is an n length string over here, we just add n plus 1 number of hashes over here, because after every character and just at the front, right? So it's 2n plus 1 length now, but it's still linear, right? If we can process this string in O of this much, we are still O of n, so we are good to go with this string too. And now in this string, you can see this is going to be a problem where we will have to solve it only for like odd centers. Why? Because let's say if you want to solve for this center, it's like solving, it's same as solving for this center, like this all these palindromes would be found out, which is similar to this, right? If you're solving it for some even center, let's say this case, you would find these over here. Similarly, for this correspondingly, you would have a center over here, and you can find this over here too. So, and now it's an odd center because there is a character at that place, right? So odd center means starting at a character and it's like of odd length. Now it's like an odd length, right? Even center means it's between two characters, starting between two characters, and it's going to be an even length, right? So that's what we do at the start to convert everything into this kind of a string, so that everything becomes an odd centered palindrome, right? Now comes the core idea of Manacher, right? So Manacher algorithm creates this p array. I mean, I just name it p array. Can you name it anything for that matter? Where p of I will tell you from the ith character in this new t string how much in the front is same as in the back, right? In a reverse way, like how much of this palindromic sequence is there. So let me give an example, right? Let's say we are focusing on this particular position over here, right? Over here. So I'm gonna fill in this one. So let's say you have one length same from front and back, two lengths same in front and back, three lengths same in front and back. Like this is equal to this, this is equal to this, this is equal to this, this is equal to this. So four length is equal on both the sides. So this would be four, right? This would be like 1, next character is not same. On this side, this is same 1, then this two are same, so 2, then third is not same because this does not exist. So this is 2, this is 1, this is again a 1 because both side is not equal. Now on this case, both sides are equal, and then after that these are 2 are not same, so this would be 2, right? And then in this case over here, this is same as this, okay, 1, then this is same as this. Let me like change color a little bit. This is same as this 1, this is same as this 2, this is same as this 3, this is same as this 4, this is same as this 5, this is same as this 6, this is same as this 7, right? So this seems like a value of 7. Okay, then let's try to focus on some other cases. So this would also give you 2, this is also give you 1, this one, let's try to focus on this one. So 1, 2, okay, then 3, 4, 5, 6, 7, 8, so they are same on both sides, 9, 10. You can see that 10 characters matched on both the sides. So this value would be 10. P of 9 would be 10 over here. So that's what we're calculating as P of I value, right? How much in the front side is like same as the reverse of the back side that we are forming over here. How much of the prefix starting over here is reverse of the suffix of that is ending over here, something like that, right? Prefix means that starts at some place and suffix means which ends at some place. Okay, so that's what we are trying to calculate, and obviously we can go ahead and manually calculate this for every index. We can just loop on both the sides and we can easily calculate this p array in O of n square, right? And that is what we are actually going to do, but in a much neater way than to convert this O of n square to O of n, right? But before that, let's try to understand why is this even helpful, right? Like if you just fill this all values, why is this even helpful, right? This is all the values, and you can check, like this is going to be helpful to calculate these two things over here, right? How will this help? Let's see. If you take this odd center over here, right, this is corresponding to this particular position over here, and you will get this as 7, right? And note that we can very simply say that for any even position, whatever you get as the value of P of I for the corresponding position in the string, just subtract 1 from that, you get the longest palindrome, because over here the longest palindrome is 6, right? Check yourself for, let's say, this position. You are gonna get 6 as well. Any other position that is smaller? I think all even centers are like pretty big, 6 in this case. For odd center, you find out this A in this sequence over here, and then you see its P of I value, and then you can simply say that P of I minus 1 is the length of the palindrome over here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 length over here. This is 6 length in the actual sequence, right? So now you can see that if you're looking at some particular center over here in the original string, you can find its corresponding position in this T string, and its P value minus 1 gives you the length of palindrome that was there in the original string, right? So that's why making this P value is going to help us solve any of these questions, right? This is fairly straightforward from what we discussed. Check palindrome, very simple. Like if you have to check from L to R, right? Simply find out the center, see what is the longest palindrome that goes in the center. If it's only less than L to R, like length is less than the length that is given to us, then this L to R is not a palindrome. But the longest palindrome that goes at this center is very, very large, then this L to R would be a palindrome, right? That's a simple way to kind of check if you have a palindrome at this particular place, right? So these two things would be fairly easy to solve in code 2. I'm not showing the code now. We'll actually code this problem, which I don't generally do in my videos. But at the end, I'm going to code all of the Manacher for you to understand and even memorize that to a certain degree. Not memorize, like understand it and actually be able to write it again if you want to. And in this case, we are going to understand this first, how to calculate this in an optimal way. But once you are done with that, these two functions should be pretty straightforward. So that's why finding this P array is the main kind of task. Once that is done, we are done with the problem. Okay. Now, how to optimize this, right? How do we optimize calculating this p array? So at every index we can go and we can kind of expand on both the sides, and that should give us the p array pretty straightforward in an O of n square algorithm. The way we optimize is, like, think about this, right? Like, let me give you an example. Think about this particular center over here. Okay, think about this particular center over here. This says that this 10 characters on this side is same as this 10 characters on this side, right? This 10 characters on this side. Okay, now over here we saw that at this center we were getting a 7 length palindrome. So in this case, some big chunk over here was same as this side, right? Now, if there is a bigger palindrome that encompasses the same zone, right, there is a very high probability that this even might have a 7 value, right? For an example, again, think about this way. Like, this center has a 4 value. Okay, this BAB is over here, right? And there is a bigger palindrome over here. So if there is a palindrome over here and this is whole as a thing is a palindrome, then this also needs to be a palindrome, right? Because it's like a reverse of this. So you can see that this 4 can actually be copied over here directly and help us to save a lot of computation where we were expanding the two sides. And that is what this optimization is all about. Okay. But again, as I said, that we have to find this bigger palindrome and then copy the values from this, right? This bigger palindrome is something that we generally maintain in implementing Manacher's algorithm, which we call as the bounding box. So let's understand how we do that, right? How we do that. So what is the idea of bounding box? So if you happen to have, let's say, a particular like center over here, right? Let's say over here, and it's, you know, that its value is 7. So this much is like kind of palindrome. So I can fairly like say, I can straightforwardly say that this position and this position are related, right? So if this position had a palindrome value of 4, right, which is like this much and this much, since this exact thing is there available in reverse, and reverse of a palindrome doesn't really change, right? So I know that this much is definitely a palindrome. So this value will be greater than equal to 4 for sure. So instead of starting from 0, I can start from 4 and then try to expand on both the sides, right? That is one very big optimization that bounding boxes give, right? Again, another idea, very simply, like when you have, let's say, a big palindrome over here, like 10, let's say you're counting for this one, right? I mean, I know that this exists over here and its value was 2. And like, since these two were same and this was a palindrome, the palindrome, like, and this as a whole is a palindrome, this much would be copied and in the reverse will also be available over here. So this needs to be a palindrome. So this value has to be 2 or greater, right? Something like this. Similarly, like this value can be copied, like this value for this center 7 can be copied over here, right? And then it might be possible to extend it a little further, but I mean, at least this much is definitely true, right? Okay. Next is, we might also get some other cases, but more or less like across this side, like if this is the center, from this side the values can be copied a little bit to this side of the whole thing, and that's what we are trying to use. See, 1 1 2 2 7 7 2 1, a lot of values are copied, right? Directly copied. So start with these as the initial value and then try to expand, is what is the hypothesis for like the optimization of Manacher's algorithm. And it turns out just this optimization makes it O of n. Why? We're gonna understand the proof very simply, but let's first quickly move to like running a little bit of like sample cases just to see how things are running. So the equation that we use over here for P of I is, P of I is equal to, obviously it will start from 0 on the worst case, right? That nothing is matched, right? If let's say you have a bounding box, right? Over here, I can see that this is gonna be like this, there is a palindrome that we found at this center, right? So from -1 till 3, both non-inclusive, right? It's like -1 till 3, like, so 0 to 2 is a palindrome, right? So r minus I is nothing but 1, right? 1. So from this, at least 1 on this side and 1 on this side is same, because this side 1 was same, right? And we can use P L plus R minus I. So this is nothing but, if you are at a, like there was a palindrome, if you are at some particular I, the reflected position will be nothing but L plus R minus I, right? Because the sum has to be same. That's, the center is exactly at the same point for both of the things. So if there is this big part, this is the center. If you are at over here, the corresponding part on this side is nothing but this plus this minus this, because the centers are at the same place, right? That's what the hypothesis of this is. So L plus R minus I is the counterpart, and with that value we can start, that can be the minimum, and from there we can try and expand. So that's the idea of this P of I value that we write over here. This is one expression that you will have to maybe remember if you want to kind of keep the code very optimal, but you can also derive it at the place if you want to. Just remember L and R is non-inclusive, right? That's what we mean over here. So we can copy this value 1, try to expand one position on both the side, but they fail, right? That's what we can have a look at. Let's say we are over here, we have filled till this particular value, and we are looking at this particular center, right? Now, L is equal to -1, R is equal to 7 in this case because the bounding box are non-inclusive. Now, over here we put the value of I equal to 6, 7 minus 6 equal to 1. Right? P of this, P of L plus R, L is nothing. So L plus R is 6 minus I, right? 6 minus I is 6 equal to 0. 0 is nothing but 1. So this is nothing but 1. So P of I will start from 1. Okay, this will start with 1. This value got copied over here. Nothing but that. Okay. But then we might do better than this, right? Because for this one, there was nothing on this side. But for this one, there is something on this side, right? So since it's at the boundary, it might try to expand it a little bit on this side, right? So we can try to see if like whatever we got, maybe if we can do a little better, right? If S of I plus 1 is equal to -1, then maybe we can do a little better than this. P of I plus plus, like 2 length now. Maybe even one more character is same, so 3 length, 4 length. Let me remove this up. 1 length is same on this side, 2 length is same on this side, 3 length is same on this side, 4 length is same on this side, 5 length is same on this side, 6 length is same on this side. The 7th line doesn't exist, so we need to make sure that we check the boundary correctly over here, okay? Boundary. But that's something we'll handle at the code. So when you're at the center, think about both the sides, keep expanding as long as you cannot go any further, right? That's what this does. And now once you have found out that, okay, hey, there exists a palindrome, which is this big over here, right? This is a very, oh, sorry, not this one. Yeah, this much, it's bigger, it's this big. We found out the value to be like 7. We need to update the LNR because now my like new palindrome that I've found, the largest palindrome that I've found that ends the farthest is going to be this one. So we always maintain this. So my new R will be equal to 13. Okay, so I will update nothing but L is equal to I minus P of I, which is the I minus P of I is the next thing that I would have checked, which means something before the current like part of the palindrome, this much before this and after this. So I plus P of I 6 plus P of I 7, which is equal to 13, right? This is over here. So I R is equal to I plus P of I. This is only thing that this is only when we get I plus P of I is greater than R. When we exceed this limit, there was the older R. If we get something better, we then update the LNR. Okay. Let's try to do it at one more case. Since say we got a 7 over here. Now we can kind of copy, like we can see for this position, this is equivalent to this from this center. So we just copy the 2 and then try to see like, can we do better than 2? No, right? So we stop. Then we copy this 1, right? And then we take for this particular node, we copy the value 4, right? So this is equivalent to this, we know directly because this one was equivalent to this much, right? Now once we know this, we should try to expand it even further, right? Because this time is equal to this. So we'll keep looping this. So it was already 4, 5, 6, 7, 8, 5, 6, 7, 8. Sorry. Let me do this again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The same things would be on this side too, in the same order, in the reverse order, in fact. So this will go till P of I being equal to 10. Oh, sorry, not this. So this will update to 5, 6, 7, 8, 9, 10, right? And then this will be the new value over here. And then since we found a very big palindrome over here, we just found a very big palindrome over here. This got updated to 10 by this plus plus. We need to update our new LNR. So that would be up till this much. So R will be equal to 19, which is nothing but 10 plus 9, I plus P of I. And this is nothing but -1. That's how we maintain the bounding box. In this problem, we are maintaining the mountain box maintains at -1, but in some other problem, it will also increase further, right? So that's there. That's something we get over here. And You can keep continuing doing this. The main idea is this is what we have as a major portion of the code. P of I is equal to max of, if let's say the other side is 0, or if there is no, if let's say your bounding box is like this and you are currently solving this position, right? Actually this will not be the case, but if you are solving this position, like this r minus I will come out to be a negative, so negative, so this will be a negative number and this will be then max to a 0. So if you're outside bounding box, by default value you will start with 0 and you will try to expand. But if you have something to copy from, just copy the value, that's it. So if you, this is the case where you don't have, let's say, some palindrome before, and this is something which is like update. If you got a better palindrome, if your current palindrome ends even further in the end, then maybe use this one as a bounding box, because all the future elements will be, best updated by this one, because the one that ends farthest from over here is one that is more likely to like affect more elements, right? So that's what we kind of use over here. Okay, so why is this O of n? Very, very important point. Try to like understand this crux idea over here. This is what is taking a lot of time, right? We are running this for I1 to n, let's say 0 to n or n minus 1 or 1 to n, whatever that is, right? Doesn't matter. This is something we are running for 0 to 1 n minus 1, right? This loop is what is taking a lot of time. I mean, ideally this might take O of n, right? But we are using this small optimization that it might just copy the value from the previous box. Why does on an armatized basis this makes this O of 1? Because very, very interesting. Okay, there is this very simple observation that we can make. See, every time over here we copied this value 4, we were touching the endpoint, right? So if we get something better, right, from this, that means our bounding box is going to get updated. Okay, so every time this executes, this is bound to happen. Okay, this is bound to happen every time we do a pi plus plus, which means we got something that was like this was the original bigger one, we copied this from this, but then this is also equal to this, right? So now this new palindrome is going to be bigger than the, like, is going to end even farther, right? So this is going to be update the rest of this, which means the r is bound to increase by the number of times pi increased. Okay, so number of times pi increases is the number of times r increases over here. Okay, and if r increases quite a lot, then it is going to do nothing but copy, right? So every time we are doing this loop, we are increasing p of I, which means we are increasing r2 over here, and r is something that is strictly increasing because we are only updating when r increases. So r can only increase O of n times. So this loop on a total basis can work only in O of n times. So this while loop on an armatized cost will give us O of n, and hence the whole algorithm takes us O of n. Okay, try to visualize this once again. If you want, pause the video, go back, listen to what I said very, very carefully. This, every time this loop works, the number of pi plus plus that it takes is gonna get added to r for sure. Think about any of the previous cases that we did. Only when it hit, when it was expanding, it got updated in the update 2. Think about this. When we got over here, we got the value 1, but then we expanded it even further, right? So it was at the r. So r got updated in this case, right? So every time you're gonna hit pi plus plus, you're gonna update r, and that's gonna give you a O of n, right? Now the rest of the part that like of explaining how the code you're gonna write and how the code is gonna look is something that I'm gonna code and explain you. So let's move to that particular portion. Okay. Okay, so let's go ahead and write the code for Manacher, and watch the code very carefully because I'm going to write it in a little modular way, and you will also remember the things if you understand why each and every step is being made. If you have not followed the previous part, definitely watch that up because that is going to give like understanding of why we are doing each step. But very simply, we are given a string s and we need to like support those two functions, right, that we had talked about. At a particular center, find the longest palindrome and check if L2R is a palindrome or not. Very, very basic atomic operation. So what we're going to do is we're going to create a struct, right? We're going to create a struct for a Manacher, right? And we're going to use the object M for that, naming very, very lazily over here, right? So we're going to create the vector int p for any particular string that is given to us, and let's say we're going to call void build for any string that we have to build this Manacher for, right? And when we get a string, we are assuming that we are not getting is pre-processed, which means the hashes are not added. So we will create a string t for, let's say, auto we're gonna go through the characters of s, right? And t plus equals to, let's say, we're gonna add the hash for the particular string, right? And then we're gonna add the character v over here. Okay, so this is gonna add all the things at the end of t. Don't, make sure that you don't write this. This is like O of n square over here itself. Please make sure to write this one. A very simple mistake people make. Now, once you are done with t, we're gonna like call the like Manacher, let's say, function, some run Manacher function on the string t, which is gonna build this array p over here. Okay, so that's what we're gonna assume, that when we run Manacher on something, we're gonna build this. Now, note that we have added hash before every number. At the end also we have to add a hash, right? So we will add a hash at the very end. Okay, so now let's write the main portion over here. So I'm gonna write void run Manacher. We will take the string s over here, and now this s is pre-processed, and now we need to do the Manacher logic over here. So integer n is equal to s dot length. Obviously, we'll just keep the length over here, and then we have to create the p array. So p array assign, we'll create an n sized array for p because of this string length after adding hash, and we're gonna assign all of them to 1, because if at every place at least one character will match, right? That is like de facto. L is equal to 1, R equal to 1. We'll start from one index because 0th one will have just one value, right? The first has, we know that it's going to be 1 because on the left hand side there is nothing, right? And 1 to 1 at least is something that is true because it's like an empty thing in this case, because you know, right? For L it's like exclusive, and for R it's inclusive, so it's like empty. Both are exclusive, sorry, so it's empty over here right now. It doesn't really matter what you keep as initial L and R, to be very honest, right? As long as they don't betray the bounds of the arrays, or you get a runtime error essentially. Let's skip that part. For now, let's go through integer number 1, I is less than n, I plus plus. We go through all the positions of this of the new string, and first of all we initialize this p of I is equal to, let's say, max of, we said 0. I mean, I think we can also do 1 if I want, but let's take 0. It will anyways update further if so. There is this while loop next, right? So if it's, even if it's 0, it will update it to 1, because this I minus p of I minus 0 is equal to I plus 0, so it will update it. No worries. Min of R minus I is something we wrote in the expression, remember? And then the other expression was L plus R minus I. So this is the two positions that we keep over here. So these, just remember this one expression, okay? Then while s of I plus p of I. Now while the next character that we potentially might have matched is matching, right? There is one big condition we had written, that we have to check boundary. So while I plus p of I is less than n, and p of, I would say I minus p of I, we just need to check with uh, 0 with 0, I suppose, right? Is greater than equal to 0. I don't think we are never gonna get bigger than n in this case, right? So while like it's why both these index exist, and if they are equal, then in that case we do p of I plus plus, right? We just keep expanding further, and if we're expanding, we know that it's going to get updated, but we will just update it only once. So if I plus p of I is greater than R, the original bounding box, then update the bounding box. L is equal to I minus p of I, R is equal to I plus p of I. And by the way, if you have understood the line till now, similar to things that we have written in the slides, you are done with the code of Manacher, right? You're already done with the code of Manacher. So over here, that's it. That's all you need. In fact, let's see the string for now. For auto, I'm gonna print the string to cout s, and for auto p in s, not s, we're gonna go through p, cout v. Right. So this is just printing the strings and stuff, and we're gonna take a string seen as. I'm gonna be lazy. I'm gonna use the same example. What was the example over here? Let's go back a little bit. BAB, 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 C. Okay, so that's a really nice example, right? Uh, BAB, right? And we're gonna do m dot build Manacher dot build s. So now we have Manacher being built for this particular string. What is this one for? No, right? So this is the whole Manacher's code. Let's run this. Let's see what this gives us. This gives us compilation error. Why? Because we have this m over here. Okay. Oh, I think I miscopied some closing brackets here and there maybe. Okay. Oh, this one I copied at wrong place. It's building for all the prefixes this time. So we have this particular string and the same thing, right? I remember 2, 4, 7, 10, seeing these exact values over here, right? So we are getting the Manacher array correctly in this case. Now, how do we use this particular Manacher array to find out the answer? Okay. So we need two functions. What functions do we want to get? So let's say we want to get the longest palindrome at a particular center and check if L2R is a palindrome or not. Okay. Int get longest at a particular center, and we want to know like if this is, so this center is like an index, right? So either it's like an odd center at this index in the original string. So this, note that this is in the original string. Okay, it's like an odd center or it's like an even center just after this character. So boolean odd or not, right? If it's odd, then it will tell us we need to find odd palindromes at this center, right? So let's take a case a, right? Or something like this. So if I give this particular thing center equal to 2 and like odd equal to 1, in this case I need to find from this what is the largest odd length palindrome. So in fact that is nothing but 1 length, right? Because you don't have a palindrome. What if we have a center at 3? Then in that case the length is 7, right? So that's what we are dealing with. Now if I go ahead and do 1 at this, the odd length palindrome is just 1 length. But if I not find odd length, it's even centered, which means I'm inclined to finding at this center, which means there is like 2 on both the sides, right? So 4 as a total would give me, this is going to be 4, right? So that's what we are like kind of dealing with over here. So now like center over here, we need to find out for this position what exact position do we go to in the like P array over here. So note that for a particular position we have like if you are index 2, there are 2 characters. Okay, so that's why this is center 2, this is position 2, right? For each one of them you will add a hash and you will add a hash at the start too, right? So the actual position is going to be equal to 2 into center plus 1, that is the number of hashes, plus if you assume this to be the center, then you get at this character. But if you want after this, then you skip this character and go to the next hash. So plus not of odd, which means if it's even, then you add plus 1 to this. That's what we are writing over here. Okay. So this is essentially just finding the corresponding position for a particular place in the original string in the converted hash character string, right? And at that place, whatever you get, p of pos is the length of that plus 1. So I just subtract 1 over there. Remember over here. So over here, like you had got like, let me go back over here. That should tell you, right? Over here at 7. Okay, for 7. Think about this. This is odd center. Let me go back, right? So for this, for 2 and even, okay, so the odd is equal to 0. So for 2, you had 2 into 2 plus 1, which is 5. But since it's even, if it's odd is 0, then even is 1. So we go to the plus 1. So that's what this corresponds to, right? So this is something you have to just formulate on your own in your notebook if you forget this by chance. But I think if you write it twice, you will remember this every time. And then for an even center, it's just 2 into the position plus 1, very similar to how we did for B. But then for even, you have to shift 1 for the next hash, right? So that's what we are doing over here. And if I go back to the code, go back over here. This is the longest palindrome that you can get over here. And checking is very simple. Boolean check palin if if the substring L to R in the original string is palindrome or not. Simply we just find out if the string that we are currently checking, if R minus L plus 1, okay, if the string length is less than equal to the longest palindrome at the same center as this string. So whatever string we have, we go to the center and then expand the maximum position that we can. And if the current length is smaller than the biggest palindrome, then this is also a palindrome. If it is bigger than the biggest palindrome over there, then it's not a palindrome. So is less than equal to get longest palindrome at the same center. What will be the center? Nothing but L plus R by 2. Very, very straightforward, right? Center. But we have to decide odd or even. So given the indexes of two things, how do you decide the length is odd or even? If the parity is same, then it's an odd length character, right? So 2 to 4, 2, 3, 4, that's a odd length. If the parity is not same, then it's even length. So simply I can write if L mod 2 is equal to R mod 2, then this is an odd length, right? Or else it's an even length. So simply we can pass this. If this turns out to be yes, we return 1, or else return 0, right? This is what we can do over here. And that should be more or less all you need to do for this particular code. And that's almost all the utility that you need for Manacher. Rest would be the problem specific logic that you need to use for a certain thing. But generally, like, we use these two things itself. Longest palindrome you can easily find now. Go through all the centers and you can check what is the best palindrome you can make, and for whichever position and degree you got, if you know that, you can maintain that, and then you can print the string too if you have to do that for certain problem. Bunch of other problems can be solved with this too. I will link some problems that you can solve with Manacher in the description below, so that you can practice this code once. And once you expertise Manacher, like, a lot of palindrome based problems becomes a little straightforward, right? So that will be all from my side in this particular video. I hope you got an idea of how Manacher works, and now you'll be able to code that, even if that is asked in an interview and you have to code it without any help, if you understand these logics very well, right? Definitely practice the problems, right? And in the comment below, definitely let me know what more topic would you love to have a video on. Please keep it a very short topic, because I know that most of you guys have been requesting me graph workshop. It's to be very honest not possible at this current moment, because the DP workshop itself like took me a good amount of time, and due to other projects that I'm currently working on in my office, I don't really have a little time left for creating and planning so many slides. So even this took me like a fairly good amount of time from some of my weekends. So already putting good amount of effort for this one. So do give it a like and share it with your friends. Subscribe definitely if you have not yet. And I hope this content is bringing some value for you all. That's all from my side. See you all in the next video. Bye bye.